Welcome to the third mini lecture for Unit 10. In this mini lecture we will be covering dark matter, and this is covered in your text in Chapter 23 Section 6, dealing specifically with the Milky Way, and in Chapter 25 Section 1. Now as we go forward, it's important to realize that what we understand about dark matter is not much, and that understanding could change drastically over the next several years to decades. So what I tell you now may not be true 5 years from now. So I will try and point out where astronomers are confident in what we know about dark matter and its properties, and where we are uncertain and not yet at an agreement on what's going on. So here's the basic outline. First, I will discuss why astronomers think there must be some large amount of unseen matter, which we will call dark matter because it cannot be seen with electromagnetic radiation. Then we'll talk about who discovered the evidence, a little bit of a history lesson, and some of the properties of dark matter, and why these properties point at our realization that dark matter probably cannot be ordinary stuff that we see around us. And finally, we'll talk about possible explanations for dark matter and specify which ones astronomers currently prefer and why. So in 1933, a Caltech astronomer named Fritz Zwicky collected some of the first evidence from dark matter. Zwicky was studying galaxy clusters, which we mentioned in our last mini lecture, these groups of hundreds of galaxies that are bound together by gravity, and he wanted to determine how much matter was there by measuring the speeds of the galaxies within the cluster. The more matter there is, the stronger the pull of gravity and the faster the galaxies will be moving around. And so this was a way of measuring how much material was there. Zwicky was then, after he measured how much matter was there from the gravitational force, he measured how much light was coming from the galaxies, and he found that there was a lot more matter there than could be explained by the light from the visible stars. And so he proposed that there must be some invisible matter, what we now call dark matter. And he was absolutely right in this. However, Fritz Zwicky was a bit of a cantankerous fellow, and he had a lot of weird ideas, although most of those weird ideas ended up being correct. So a lot of astronomers didn't pay any attention to him at the time with his fellow astronomers, and he didn't think very highly of them all the time. In this case, and in many other cases, he was correct. There was some matter here in these clusters that he couldn't see. However, for the next 40 years until the 1970s, no one really paid much attention to Zwicky's findings. In the 1970s, an astronomer named Vera Rubin, who's still around and still doing some research, although she's mostly retired now, she was doing some work to measure how fast spiral galaxies rotate, and she used the Doppler shift. So here's a picture of Vera Rubin measuring how fast the galaxies are spinning. She used a microscope to zoom in on photographs of spectra. Today we would do this all on the computer. She didn't have it that easy back then. But if we look on the right, you can sort of see what Vera Rubin was looking at. So at the top is a picture of a galaxy, and then the line indicates where we're getting the data from, a line across the galaxy. And so you see if this is a normal spiral, it will be spinning with the right side coming toward us and the left side going away. Down below, you see the spectrum itself, and we're looking at the emission line of a particular type of gas. And what you can see in these two emission lines is that indeed on the right side of this galaxy, the light is blue shifted, so it's coming toward us, and on the left side, it's red shifted, it's going away. And by how much it's blue shifted and red shifted, Vera Rubin is able to measure how fast the spiral galaxies rotate. And then, very similar to what Zwicky was doing in galaxy clusters, she used that information to determine how much matter there must be in a galaxy and compare that to what we can see in the stars and dust and gas. And what Rubin found was that the spiral galaxies are rotating faster than gravity alone could explain. Gravity from the stars and gas that are visible alone could explain. This picture is a terrible picture of a galaxy, but superimposed on the bad picture is a plot, and the plot shows how fast the galaxy was spinning as a function of distance. And that's the yellow dots, and the error bars on there show the uncertainty. So you can see that the further out you go, the faster it's going. However, if you take all of the data that we know from the visible stars, from the gas that we can measure, from the dust that we can see, and predict how fast they should be going, that's the dashed blue line down below, which is a lot slower than what we see. So again, the only way to explain this would be if there is additional material that we don't see, or dark matter. So Fritz Zwicky and Vera Rubin, they both found evidence of objects moving faster than gravity alone could explain. Today there are many other lines of evidence to suggest that dark matter is real and it's ubiquitous. It appears that almost every single galaxy is surrounded by a large halo of dark matter, and that there's 6 times as much dark matter in a galaxy as there is ordinary matter. That's the amount of gravity we need to explain these spiral galaxy rotations, to explain how fast galaxies are moving in galaxy clusters. And we've now been able to look in every part of the electromagnetic spectrum for any possible material that we may have missed, and we just don't see it. So what are the possibilities? What could dark matter be? Well, the first one, and the one that would be the least controversial, is that dark matter is ordinary matter, ordinary atoms, that are just not in the form of visible stars and visible gas. Things like perhaps brown dwarfs that have cooled off so that we can't see them, or planets that aren't anywhere near a star so they don't reflect any light, or maybe even miniature black holes. If black holes are not near any other material, that material will not be spiraling into the black hole, so it won't heat up for us to see. So there are many possible forms of ordinary matter that don't give off much, if any, light. However, astronomers have pretty much ruled this out now for several reasons. First, they looked for these objects, because even though they don't emit light, they still have gravity, and that gravity should affect the light from other stars or cause nearby objects to move in funny ways, and these searches have come up empty. We don't see any excess of invisible objects. Second, the Big Bang Theory makes predictions that have been borne out in observations, and we'll be talking about this in a couple of weeks. But the Big Bang Theory predicts how much ordinary matter should be in the universe, and we see that much ordinary matter. If we tried to add more ordinary matter, more atoms, even if they're in the forms of rocks or planets or stars, or brown dwarfs that we can't see, then the Big Bang Theory would no longer work. So these lines of evidence and a few other even more complicated ones that I won't go into suggest that dark matter cannot be ordinary matter. So we can pretty much rule this out. Another idea is that perhaps dark matter is a failure in our theory of gravity, and right now we use Einstein's general relativity as our main theory of gravity. Now this is completely possible, however, relativity has passed every other test it's been put to. Now it doesn't mean that it can't fail this one. But if you're going to get rid of relativity, you need something else to replace it. And all the alternative theories that have been proposed cannot yet make detailed predictions, or if they do make detailed predictions, they still don't show dark matter. So right now we have no good alternative to Einstein's theory, and those few alternatives that have been proposed, they don't work any better than relativity. So a third option is that there's some type of matter out in space that doesn't interact with ordinary matter, so it doesn't interact with the atoms that make us up, and doesn't interact with light, which is why it's invisible. Now this is currently the hypothesis preferred by most astronomers, and also by a lot of physicists, and there are several reasons for that. First of all, some hypotheses, some theories of particle physics that have not yet been proven true, but that a lot of particle physicists like these theories. They predict subatomic particles, so very tiny particles, that have properties very similar to some of the properties of dark matter. And they have all kinds of names that all mean basically the same thing. The name just depends on what theory it comes from. But these are things like WIMPs, which stand for weakly interacting massive particles, WIMPzillas, which would be very heavy WIMPs, axions, supersymmetric particles, neutralinos. There are just a ton of different names of weird exotic particles that have not yet been proven to exist. However, these particles should every once in a while interact with normal matter, very rarely, but on occasion. And so there are searches underway to find these particles. There have been some news stories in the last few years of some of these searches announcing preliminary results that offer tantalizing hints of dark matter, but none of these have come close to these scientific standards of proof that we would like to see. But I would say that these searches are now getting sensitive enough that if in the next decade or so they don't find weird particles, then this preferred type of explanation for dark matter will start to get very uncomfortable. So let's summarize all of this together. The main indications of dark matter, the main reason that we think we need some sort of matter that we can't see, came from observations of how fast objects are moving due to gravity. The first evidence was put forth by Fritz Zwicky in the 1930s when he measured how fast galaxies and galaxy clusters were moving, and he found that they were moving too fast. Then in the 1970s, Vera Rubin showed that spiral galaxies rotate faster than could be explained by the stars and gas alone. And these data put together convinced astronomers that there must be something out there that we call dark matter. Now, in the meantime, there have been many other lines of evidence, most of which require some fairly detailed physics to understand, but this evidence basically points that dark matter cannot be ordinary particles, cannot be ordinary atoms, protons, electrons, hydrogen, helium, uranium, can't be asteroids or black holes or anything like that. That whatever this dark matter is, it can interact with normal matter only by gravity, and it doesn't interact with light at all. Now, the best explanation that astronomers have for this is that it's some sort of new subatomic particle that hints at physics beyond what we currently understand. However, we haven't yet proven that such a new type of subatomic particle exists. Searches are underway, and if these searches do not succeed in the next decade or so, we'll really start to question this. About the only other option remaining is that gravity works differently from the way that our current theories of gravity say it should, but as of right now, there are no good alternatives that work. I wish I could tell you more about dark matter, but really, this is sort of all we know. There's about 6 times more dark matter than there is ordinary matter, and this is disconcerting that out of all the stuff in the universe, the stuff that we can see and that we're made out of and that our society is built on is only about 15% of the material that's out there. And later, in the next unit or two, when we talk about dark energy, we'll find out that there's even stranger stuff called dark energy that we have even less of a clue what it is, and it seems to make up most of the universe. So for now, go ahead and finish the response to this mini lecture, and then proceed on to our final mini lecture on galaxy collisions.